Okay, this is a short lesson on inclined planes. An inclined plane can be something as simple as a ramp, or it could be a slide that you slide down. It could be a part of a roller coaster. It could also be a ski slope. Any of those are classified as inclined plane problems. And I want to go over how to draw the force diagrams and how to calculate the components of the weight that act down the incline and perpendicular to the incline. This angle theta is often called the angle of inclination. So let's draw a free body diagram of this mass that sits on the inclined plane. So the first force that we usually draw is the force of gravity. So let's draw an arrow straight down. That represents the force of gravity. And then the other force is the normal force, which is perpendicular to the surface. So because the surface is not flat, we need to draw the normal force so that it's perpendicular to the incline. Now our coordinate systems are usually vertical and horizontal, like so, but this is so much easier if we rotate our coordinate system so that the x-axis is parallel to the incline and the y-axis is perpendicular to the incline. So now the normal force lies along the y-axis and the weight still acts straight down. If you noticed, this angle right here is the same angle as the angle of inclination because we rotated the coordinate system the same number of degrees of the angle of inclination. So this angle and this angle are the same. Now we know if there's no friction, this box is going to slide down the incline, but it's not obvious which force actually acts down the incline because there has to be at least one for it to move that way. So we have to look at the weight, and we have to resolve the weight into components that are parallel to the incline and perpendicular to the incline. So let's do that with these two arrows. This represents the component of the weight that's parallel to the incline. Then this represents the component of the weight that is perpendicular to the incline. And we're going to call these FGX and FGY. If this box will get out of the way. Now, no matter what's going on in this kind of scenario with inclined planes, these two forces and the two components of the weight will always be present. It doesn't matter whether the box at rest because of friction, whether it's sliding down the incline, whether it's sliding up the incline, whether it's being pulled down the incline or pulled up the incline. These forces will always be here and will always be directed down the incline for the x component, perpendicular to the incline for the y component. They will always be there. You need to remember that. Now if we look at this right triangle and we know the angle and the mass or the weight, we can find the y components and the x components by just using some trig. So FGY is FG times the cosine of theta, and FGX is FG times the sine of theta. Now if there are no other forces acting on the box, then the one force that acts down the incline and causes the acceleration of the box is just FGX. And if you can plug this in your calculator, but as theta goes to a bigger and bigger number, reaching a maximum of 90, the force acting on the box goes towards Fg, because the sine of 90 is 1. And of course, if that's the only force acting, then the acceleration will be the acceleration due to gravity, because if this is 90, then basically the box is in free fall. So let's look at a simple example where we place a 2 kilogram mass on an incline and we let it go, and the angle of the incline is 25 degrees. So applying Newton's second law, there's only one force that acts in the direction of motion, and that is Fgx. So we have Fgx is equal to ma, but remember also that Fgx is mg sine of the angle, so that will equal ma. And if you notice, the mass doesn't really matter because there's a term, an m term on each side. So the sine of 25, that is g sine of 25, equals the acceleration. So when we do the math, 10 times the sine of 25 is 4.23. So the acceleration down the incline would be 4.23 meters per second squared. Alright, in this example, we're actually going to apply another force up the incline, and we're just going to call that F. And let's say that F equals, so we'll say that the applied force here is up the incline and its magnitude is 15 newtons. We'll also say the mass is the same, 2 kilograms, and the angle is still 25 degrees. So as always, the first thing we do is draw the free body diagram, which we have here, and then apply Newton's second law. Now I know that the mass is going to accelerate up the incline, so I'm going to take up the incline as positive. So applying Newton's second law, the equation would look like F minus Fgx, and that's going to equal ma. So here we have the equation, and we need to solve for the acceleration. So dividing both sides by m, I get F minus mg sine 25 divided by the mass, and when you plug in the numbers, you get 3.27 meters per second squared.